Yeah.
Do I have to read the question?
Yeah.
Use Planck's constant 6.626 times 10 to the negative 34 to solve the problem. What is the amount of energy carried by the frequency of 5.71 times 10 to the 14th Hz, oh my god, D, thorium, wrong one, 3.78 times 10 to the negative 2.
That is correct.
Can I ask you a question?
Yes.
Okay, I'm just on 9. On the study guide, it said A was correct. What said that version was correct? It's marked wrong.
Yeah, that should be.
And then on 4 read, the study guide also said B was right, but
Well, yeah, A should be the correct answer.
I get it marked
yeah, it's
wrong.
marked wrong.
Yeah. I don't know what's going on there. There's
And is B the correct answer for 7? Because that on the study guide it also said that one.
so 9 is wrong, and which one B?
B on 7. Yeah.
Number 7.
Yes.
B should be right for 7. They're
Yeah.
saying A. Yeah, it was. That's an error. I don't know what's going on with the.
So 7 and 9.
Yeah, both of those.
You want us to mark them right?
We'll go over them here, and I'll address it here in a minute. I'll probably just change the curve a little more.
Okay.
All right, go ahead.
Which element has an electron configuration 1s2s, 2p3s, 2p4s, 2p? I said D, chromium 4.
Correct. And number 6. I go to F.
Number 6, which is the frequency of the wave shown? I had C, 125
Okay, everybody agree with that?
Yep.
All right. And number 7 is one we changed. 7 should be B. And number 8. Everybody get 8?
I couldn't get 8. Remember
Okay,
I
it
originally
says-
did it on the test? I counted out 4, but then there was only 3, 1, 2, 1, 0.
Okay, so if we look at sulfur, how many valence electrons does it have?
6. No.
Oh, it has
Yeah, 6.
Yeah, 6.
Right, so it's in the same group as oxygen. So we're going to have 2 unpaired.
Oh,
Should
is
be
it talking
2.
about the dot function?
Yeah, there should be 2
I thought it
unpaired.
meant in general. That's why I added up 2 more because of the ones in the first energy level. Those would be unpaired as well.
Well, in the first energy level, they are actually paired up. Helium is behaving like a noble gas. They pair up.
They are.
Yeah. If you looked at the periodic table that I gave you before, they should be paired up. Yeah, there's 2 of them.
Given more credit than Mayer because he published his organization first, like Newlands.
Was published by John Newlands in 1863. And Belwar, question number 1, what did John Newlands propose but not prove? Points?
Oh wait.
Oh,
What did John Newlands propose? Yesterday we talked about this, but he didn't prove it. Starts with a P.
Periodic relationship.
That's close enough, Garrett. Periodicity. He proposed periodicity. Remember we took notes on that? So up here, we've placed the group and the period just so you can have a comparison to the periodic table that we currently see. And if you note here, only hydrogen, lithium, and magnesium are placed correctly compared to the current periodic table. Now, what we want you to note is how the charges are shown based on what John Newlands published. If you look above the same table, he's got sodium, potassium, rubidium, cesium going across. So his pattern would be the first row is going to be -1. The second row is going to be +1. The third row, +2. Fourth, +3. Fifth, +4 or -4. Sixth, 3 negative. And then the 7th, 2 negative. So he doesn't really have this nice pattern we see in our current periodic table. So this would be 1 negative. See fluorine. Fluorine's obviously 1 negative, right? Y'all familiar with that now? 7 electrons. Lithium and sodium, we only have 1 electron, so that's going to be 1 positive. See the pattern there? 2 positive. Calcium's 2 positive. Aluminum would be 3 positive because it has 3 electrons it wants to lose, right? And then we have carbon has 4 positive. Nitrogen, 5 electrons around it, so it's 3 negative, wants to gain 3. And then oxygen is 6, so wants to gain 2, right? 2 negative. So he's got his columns, the rows, the charges going across instead of down. Are you familiar with the current periodic table where the charges go down?
Yep.
This one's going across. So everybody note that? If you remember from yesterday where we had the musical scale, right? And the whole idea behind the musical scale is to note that patterns repeat themselves, like C, D, E, F, G, A, B, and then I guess we would say the next higher first note. And then it continues on, C sharp. So there's 7 octaves on a piano, right, that they repeat themselves. Is everybody familiar with that? Well, you don't get that repetitive pattern in these first 2 tables. So he's not proving periodicity. He's proposing it, but he just hasn't figured out how to organize it. Does that make sense? Okay, so this is the periodic table that Mendel published in 1869, and it's following the same pattern that John Newland's followed, that he has the charges going across the group. Fluorine, chlorine, bromine. Periodic table. This is the periodic table of 1870. However, he's still doing basically the same pattern. If you look at period 9, you'll see fluorine, chromine, bromine. The pattern is still going across. He is leaving question marks here. He's proposing, that there's some elements missing, and he wants to try to figure out what those elements are. Developing the periodic table. So the major change comes in 1871, and it happens this table. And the reason is he gets a lot of credit for developing the periodic table is that he switches the direction of the charges. He now places them where they're going to go down a group instead of across. And you can see that here with hydrogen. See how lithium is 1, sodium. See that pattern there? Potassium, magnesium, calcium, 2 positive, aluminum, carbon, nitrogen. See how he's really picking up the pattern now for the current periodic table? This is really important because this is what establishes the periodicity, the repetitive pattern that we see in the periodic table. Whereas the second period is following the same pattern as the third period. And the fourth period follows that pattern for the main group. The main group really are what we use to predict the future as far as what the elements are going to do. Without the main group, the periodic table really is not really useful at predicting things. So this is where Mendel gets a lot of credit. And he is a Russian, so everybody say go Russia. What did Moseley do? Oh, anybody help her out?
It's A, right?
What?
He did some with the atomic number.
He determined the atomic number. Very good, Heather. Thank you very much. The atomic number is very important because it determines the look of the atom. Gold looks the way it does, platinum looks the way it does. You look the way you do because of the protons. Your DNA just organizes the cells so that protons can determine your look. So keep that in mind. You're made of these atoms. Now, this is the last point here, 10 points. What did Henry Moseley use to determine the atomic numbers of the elements? Raise your hand. What did he use?
Is that right?
What?
You're gonna go on.
No.
Start it.
Starts with the E. Raise your hand.
Electron.
Heather, very good. He used electron. Raise your hand next time I give you half credit.
Fixed time 10 to the -34 to solve the following. What amount is the energy carried by a photon that has a frequency of 5.71 times 10 to the 14th?
Which looked from 1830 to 18.
Number 4, I've shown you the math to solve for it. Basically, you're solving for energy. This is Planck's constant times the frequency. And once again, what does Planck's constant stand for, Lily?
I don't know.
Anybody? 5 points? I'll give you 10.
What are you talking about?
What does Planck's constant represent? 10 points?
Oh, I wrote about it too.
15 points. 25 points.
Dang, that's a lot of points.
That's a lot of points.
Oh no.
If you can tell me what Planck's constant stands for, what does it represent? No?
Wait, does that have anything to do with like wavelengths and stuff?
Maybe.
It does. That makes sense.
5 seconds. 5.
No, say the
4.
question again. What is it?
What does Planck's constant represent?
Planck's constant, like the constant.
What does the
wavelength.
energy represent?
The energy represents like
The wavelength.
The action of
Frequency.
The speed.
No.
atoms.
the volume. I don't know.
Frequency would be defined as hertz. Brendan? No, that's frequency. Now, shh. Planck's constant represents the minimum amount of energy that can be given off from an atom. So if you remember, we talked about the Balmer, the Lyman, and the, what was it, the series? Balmer, Lyman, and the, I didn't memorize them. Well, it's associated with an electron, and when it's pushed into the lower energy level, you don't need to memorize everything in the encyclopedia. You just have to understand what's going on as far as patterns are concerned so you can make money. So if you remember in chapter 5, when we were moving the electron, when we did the flame test lab, that's kind of what's going on with the Planck's constant. As you see here, you have Balmer, Lyman, and the Paschen series. So the Planck's constant is the minimum amount of energy that is produced. So up here, what you're going to do, you're going to multiply these two, and the answer would be E. All right, who can do number 5?
Actual mass is up here. I put D.
That is correct. And 13? All right, Vance. All right, Austin.
Which of the correct number of valence electrons do I put D.
And number 14? Let's go with Christian.
What is the next atomic order in the series? I said C.
And 15? Diane. That is correct. 16. All right, 16's on the board up here, where you have the frequency, correction, the formula that I gave you on the test, E energy equals Planck's constant times frequency. You're solving for the frequency, so you're going to take the energy in joules divided by Planck's constant, and whenever you divide exponents, you subtract them, so negative 24 minus 34. So it's going to be 24 plus 34, negative 24 plus 34, and you're going to get 9 from that. So try that on your calculator. Number 17. Vance. And 14. Let's go with Melanie.
What is the next atomic orbital in the series? And it's C4.
15. Let's go with Naomi.
A photon is emitted from an atom with an energy of 4.25 times 10 to the negative 19 J. What is the wavelength of a photon? Is it A, 467 nanometers?
And 16. Let's go with Annette.
What is the approximate frequency of a photon having an energy? I'm not reading all that. And D, 8, X, N, HC.
That's pretty lengthy. Okay, so on the board up here, I've got some help for you if you didn't get this one right. So 16, the formula is energy equals Planck's constant times V, where you solve for 8 times 10 to the 9th. It's basically a division problem. Whenever you divide exponents, you add them. Correction, you subtract them. So you're going to subtract negative 24 minus negative 34, which makes that a positive 34. When you divide exponents, you subtract them. So for 5 points, Planck's constant, what does Planck's constant tell you? 5 points. We talked about this last week.
Wait, repeat it again.
Planck's constant. What does it define, or what does it tell you?
Can you give us a hint?
Is there where something's gonna be?
Close. I'll give you a hint. The flame test.
Predicts the future.
No.
Bless you.
It's a pattern.
No.
Next what color the flame will be.
What does it start with?
The flame test is an example.
One quantum of
You looked it up.
electromagnetic radiation of the frequency of
It's
that
on his
radiation.
tablet.
Wrong.
Okay.
Wrong.
I said it was an energy.
Who's cheating, Jimmy?
You're close. If you remember,
Go back to facilities.
if you remember the flame test. Yeah, you're close. If you remember the flame test, and you got different colors, you got red light, and you got blue light. The red light is associated with the 3 to 2, so you move the electron from the third energy level to the second. And the blue light is the 6 to the second. So the further you move the electron, the greater energy is given off. But there's a minimum, and the minimum is Planck's constant. Planck's constant is the minimum amount of energy that will come off when you start moving an electron. Remember the video we showed you, and they were moving the element or the molecule, and it was giving off energy? This is the minimum. It's 10 to the negative 34. That's kind of low, if you didn't know. How low can you go? That's pretty low. Negative 34. Ethan?
Which is the correct number of valence electrons in the element sulfur? A, 6.
And number 3? Alex?
The principal quantum number indicates what property of an electron. C, energy level.
And number 4?
Yeah.
Koenig?
Use Planck's constant 6.626 into 10 raised to power negative 34 to solve the following. What is the amount of energy carried by a photon that has a frequency of 5.71 into 10 raised to power 14 hertz? The answer is D, 3.78 into 10 raised to power negative 98 joules.
Okay, so number 4, if you were having trouble, Noah, with number 4, up here on the board I've given you an example. You're solving for the E equals Planck's constant times V, which would be frequency, and you take 6.62 times 10 to the negative 34, multiplied times 5.71 times 10 to the 14th. So when you multiply exponents, you add them, and you'll see that negative 34 plus 14 decreases the exponent value from negative 34 to negative 19. Now, for 5 points, I'll give you 10. 10 points if you can tell me, what does Planck's constant represent?
A number.
Well, obviously it's a number. What does that number represent, Ethan?
The variable.
No?
Frequency.
Raise your hand.
Frequency.
No, we've talked about this before. We talked about when we discussed the energy given off in the flame test. Close?
Photon.
No?
The appearance.
No? Okay.
The electron. Power of the electron.
Close?
Proton.
No. Now, if you look up here, 10 to the negative 34 is extremely small. Like 0.5, a lot of people think half is small. We're talking about 10 to the negative 34. That's the zeros that are going to be in front of that 34. 10 to the negative 34. There are like 33, 34 zeros following the decimal. Shh. Are you following that? That's a very small amount. It is the minimum amount of energy that's given off when an electron is moved. If you remember the video we showed when we talked about Planck's constant, they assumed there was not a minimum, and they couldn't figure out values. They couldn't calculate values. So they had to determine the minimum to calculate or find unknowns. So right here, we can take Planck's constant and we can determine the energy given off. So it's the minimum amount of energy given off when an electron is moved. Remember, temperature is a measure of what? Movement. On the overhead, you can see that if you have 20 waves in 1 second, that's associated with 20 hertz. Does everybody see this? 20 waves in 1 second is 20 hertz. So when you're asking you questions about hertz, they want to know how many waves are in 1 second. looking on your quiz here, you go to the 1 second, which would be half of the 4, which is 2, and half of the 2 is going to be around 0.125 waves per second. Over here, you're going to go to the 1 second, and you're going to see how much of a wave you have. That's where you see half a second, or half a wave per second, which is D. So when you see hertz, they're specifically only talking about 1 second, as you see right here, where it says 20 waves in 1 second, waves per second. A second is not a lot of time. I mean, seconds go very quickly. 1,000, 1,000, that's a second. 1,000. For us, a second is not a lot. Now, for energy, a second is a long period of time, because waves can travel very fast. But compared to us, we don't travel as fast as waves do. We don't run as fast as they do. Well, that's a biological thing. You can't run as fast as, like, let's say, a wolf or a bear. No. Well, probably. There's a lot of advantages. And 21? Courtney?
Do I gotta read the question too?
Yes.
Look up you. These Planck constant 6.626 times 10 to the negative 34 power. To follow the solving problem, which amount of energy carried by a photon that has a frequency of 5.71 times x 14 power. It's D 3.78.
All right. 4 is D. I've got it up on the board up here. If you need an example, right here, number 4.